Hello, my name's Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering, and this is an introduction to the hands-on lab exercises in ENCM 370. So, the learning objectives I have for these labs is to give what is probably for most of you your first exposure to embedded design. And unlike, and this is maybe where electrical engineers kind of deviate a little bit from software engineers. So you're learning how to program just like in software engineering. But one thing that electrical engineers do that is a little bit unique is to work with what's known as mixed signal design. And this is basically creating designs with analog and digital electrical components. Now, the goal of ENCM 370 is to introduce you to what's known as embedded design, where you embed, as the name suggests, a microcontroller unit into a broader electrical circuit, electrical engineering design. And this type of embedded mixed signal design is everywhere. So the computer in a smartwatch, the computers in cars, the computers in toys, the computers in appliances, all of these would be considered embedded designs because they have a microcontroller that's been programmed in the product, but it doesn't look like a laptop, right? Like it doesn't have a a screen or a keyboard, but it still is programmed and just like you've been programming your laptops up until now. Now, this is the reason why there's a bunch of reasons why I want to focus on embedded design, but embedded design is probably the way that the vast majority of you will be applying what you learn in ENCM 370 in industry. So in the 370 lectures, we're going to learn how to create a microarchitecture. We're literally going to be building a little digital machine that runs codes out of flip-flops and basic logic gates. Now, this is exactly what engineers do when designing the new NVIDIA GPUs, when designing, the new ARM core processors. You have a whole bunch of engineers working at like the logic gate level to create these digital architectures. But to be completely honest, getting those types of jobs straight out of undergrad is relatively rare. Most of the people I think working in this field probably have graduate degrees. But it's way more common to get a job designing hardware that incorporates some kind of embedded microcontroller. So for example, to use a local example, Calgary's oil and gas industry is a significant employer for us. And there's a ton of embedded design in the oil and gas industry. All of these sort of sensors and tools that are developed to monitor oil and gas extraction and processing, so many of them have embedded designs. And as you're going to see, understanding the microarchitecture of a microcontroller is an important part of being able to use it effectively in an embedded design. Another thing I want to say, kind of right at the start, is that these are not programming labs. So don't think of these as programming labs. Now, you will, of course, be writing some C code, for sure, in the labs. But the main challenge, the main problem you're going to be learning how to solve is how to use software to control how our AVR microcontroller reads and generates external analog and digital signals. So you're actually going to be using software to create digital signals, to create analog signals, to read those signals into the microcontroller and respond to them. And it's that sort of interface between your chip and, let's say, the real world or the rest of your electrical engineering design that we're really going to be focusing on. Most of the programs that you write for this class are going to be really short, probably 20 lines or even less than that. And you will actually spend way more time reading the AVR data sheets to figure out exactly which lines of codes you could write. So instead of calling these programming labs, I would actually call them datasheet reading labs. So you're going to get really good at reading the AVR datasheet and understanding the sections in there and what it's trying to tell you. And, this is pretty consistent with how embedded design works in industry as well. So, embedded designers don't write millions and millions of lines of code. They tend to write a relatively small number of lines of code that are right, close to that interface. And that's kind of consistent with the experience that you'll be getting in these labs. So, as I said, the datasheet is key. And in each lab, in the handout for each lab, I'm going to be providing you with a list of sections that you should focus on in the datasheet. So the datasheet's really long, right? It's hundreds of pages, and I'm not expecting you to start at page 1 and read it through all the way to the end. I am, however, going to be recommending certain sections from the datasheet that you should read for each lab, and it's really important that you read these. Like, there's basically going to be no way we can help you if you haven't read these datasheets, because you just need to know the information that's in there. But at the same time, datasheets do get some getting used to, and they contain a lot of information, and the trick is to sort of scan the data sheet and sort of figure out where, you can find the information that you need. But this is hard, right? This is a skill that you need to develop. And this is one of the things that you're going to be working on in ENCM 370 is learning how to kind of make friends with data sheets like this. And so it's going to be something that we're going to help you with. I'm going to guide you as much as possible. But at the same time, I really did want you to work with the real data sheets. Like, I suppose I could have extracted information from the data sheet and somehow, softened it or made it easier to digest or something like that. But, it's really important, especially as you're thinking about going out on internship, maybe to have the experience of working with a real device and a real data sheet and putting that in a design that you create. So the specific microcontroller that we're going to be using is the AVR 128DB28. The reason why I've chosen this device is that it's got a relatively simple 8-bit architecture, so that's nice for us to talk about in the lectures. And it's also really cool to use in design labs. So it's you can get it in a dip package, so you can squish it right onto a breadboard if you want to. It's really tough. And it's kind of like a little Swiss Army knife. It's got a huge number of different peripherals in it, as you're going to be learning about in the labs. And this type of chip would, if you saw it in industry, it would be for, very small kind of low power designs. So this type of chip uses hardly any power. It could run on batteries for a hugely long time, but it's also relatively simple. So it can't do like a bunch of MATLAB style signal processing. You can't get AI running on these chips or, voice recognition or speech recognition. And we also won't be working with a lot of predefined libraries. So if there might be some of you that maybe have a bit of experience working with Arduino devices, where, if you've got a nice peripheral for it, there's usually a library that you can call to work with that peripheral. The reason why we won't be using libraries is because really in ENCM 370, you're learning how to write those libraries, right? Like, somebody had to create those libraries to work with the chip at a low level. And that's basically what we're learning in 370. The way that you are going to be, the way that your program is going to be sort of communicating and interfacing to the outside world is through something called special function registers. And Special function registers, when you're writing C code, are basically special variables or variables with special names. If you write to one of these variables, if you assign a value to one of these variables, it's you essentially write a value to the special function register. If you read a value from its C variable, that's equivalent to reading from the special function register. And so, for example, the pins on port A in the microcontroller can be configured as digital outputs if you write a 1 to different locations in a special function register called dir set. So there's literally a variable called port A defined in the C programs that we'll be working with, and then you just go dot dir set, and that allows you to access the dir set special function register. And so if you want to set some of your port A pins to outputs, you copy a value into that variable in your C code, and it sets the appropriate pins in the special function register. All of these special function register variables are available and defined in a special header file, and I've included that header file in your in the lab 1 folder. But again, these special function registers are basically special variables, and you'll be reading and writing reading from them and writing to them, and that's basically how most of your programs are going to work. The development environment is provided by Microchip, the maker of the AVR chips, and it's called MPLAB X. It's free, it works on Windows, Mac, and Linux, and I've got instructions in the Lab 1 folder for downloading and installing the MPLAB X environment. We're also going to be using it for the assembly language part of this class. We're going to literally be writing assembly code in MPLAB. And so you can install MPLAB on your laptop. You're going to be working on the labs in partners, so technically only one of you needs to have this working, but probably you both want it working. And to program the AVR chips, you're going to need a USB port and a snap programmer, which is something that we're going to provide to you. So it's this little dongle that plugs into your USB port, and then you connect it to certain pins on the AVR board. And so how do you get help in these, when you're working on this stuff? Because this is a significant learning experience. You've all got programming experience now, but you've only probably, most of you, programmed laptops. This business of programming a little chip that doesn't have a screen or, an easy way to sort of see how it's doing is a whole new experience. And, it's something that we're going to be, walking you through as part of the lab exercises. And there's going to be lots of chances to ask questions. And so the main place where you're going to ask questions and get help will be the in-class studio sessions, and we don't have drop-in sessions this year, but basically the lab sessions. So every week we have 4 hours together, right? We've got the three lecture hours all sort of jammed together in one time slot, and then right after that we have the lab times. And in the studio sessions, the first part of the studio sessions are going to be doing the in-class assignment and talking about the lectures. But, most weeks we're probably going to have at least an hour, sometimes more, left over at the end of the studio session for you to basically work on the labs. So you've got part of the studio session and all of the lab sessions every single week to work on these labs. And, the TAs and I will be there to give you a hand. But if you put up your hand and ask for help, we will always ask you first, what have you done so far to troubleshoot your problem? So active problem solving is a requirement in ENCM 370. And you always have to have made some kind of an effort to troubleshoot your problem before the TAs or I will help you. And I'm instructing the TAs to work in this way. So, you won't be able to just sort of say, hey, this is broken, please fix this for me, and have no idea what's going on. You will have to be able to describe, how you've troubleshooted things, some things that maybe you've ruled out, and then we'll, help you along and give you a hand. Outside of class, you can always post on the D2L forum. And if you're posting about labs, don't be afraid to take some pictures, upload some screenshots, stuff like that, and I'll be able to help you if it's outside of class time.